Well, we'll get started. Good morning, everyone. Welcome to Toronto. Welcome online. Thanks for joining the meeting. So my name is Ziggy Pleunis. I'm a Dunlap Fellow at the University of Toronto and also a chair of the organizing committee. We're very excited that all of you are here, very overwhelmed and very happy with the excitement for this meeting. I'll be saying a few words before we get started with the first session. So you are at the meeting multi-wavelength follow-up of fast radio burst in the era of routine sub-arcsecond localizations. It's a mouthful, but I hope everyone here is very excited for this topic. So how this came about is in one of the time FRB meetings, we were talking about the prospects for building the outriggers that we're currently constructing. What is the science that is going to enable? And then we started worrying there's going to be a lot of challenges as well. We'll get hundreds of localized FRBs, and we would want to know redshifts for all of those. We want to zoom in with Hubble or JWST and find the local environments. We want to do X-ray follow-up. We want to do more radio follow-up. And that's obviously going to be a lot of resources that we need, and there's going to be other telescopes as well that are localizing FRBs, so we should strategize together, and that's how this meeting came about. And we suggested let's do it in this nice building on the University of Toronto campus. So the meeting is organized by the Dunlap Institute for Astronomy and Astrophysics and the Chime FRB collaboration. We got financial support from the Dunlap Institute and from MIT, and we wanted to keep it easy for people to join, and that's why there were no registration fees. But that's only due to this generous support. As I said, very excited about everyone who wanted to join. There's 63 in-person participants here today and tomorrow from 6 different countries, and then an additional 61 remote participants also from 16 different countries. So it's very, I'm happy a lot of people from all over the world are joining the conversation, and we can really strategize together, as was the intention of the meeting. Before we delve into the science, we wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. In this context, I always think it's important to realize that we as astronomers, we hold power. We are the ones who decide who gets to be an astronomer as well, who joins these meetings and who joins our field. And we should take the opportunity to think about how we can be better at wielding our power. The organizing committee for the meeting, the scientific organizing was done by the 5 people in the top row. So Jane Kasmerick unfortunately couldn't be here today. She's joining remotely because she recently took up a new job at CSIRO, and she's moving. Adam Lemon is here. He's a postdoc at McGill. Kenzie Nimmo is a postdoc at MIT. That's me. And then Paul Schultz is also a Dunlap Fellow at the University of Toronto. Our name badges have this nice little colored dot. If you're looking for us, please let us know if you have any questions or tell us how we're doing. And then we were helped for the local organizing by Amanda Cook and Ayush Pandey, who are both graduate students at U of T. They're sitting here in the front row. They'll be doing the Q&A microphones. And then Karo Menovich, you'll be seeing once in a while. She's the events organizer for the Dunlap Institute. She also helped us a lot. So for the logistics, I'm happy all of you found the building. All the talks and all the discussions will be in this room. And on Zoom, and we'll use the same Zoom link throughout for the people online. If you'd like to ask questions, there's the Slack channels for each separate session. You can raise your hand in the room or on Zoom. And everyone on Zoom, it's a meeting, so everyone should just be able to speak up if they'd like to. But please don't do that during the talks. If you're in the room, please wait for a microphone to be handed to you so that the people online can also hear you ask your question or give your comment. This is only for tomorrow, but for some of the discussions, we'll do non-hybrid breakout sessions. So we'll break out separately on Zoom and in the room and in the room next door. And then we'll always come back in a plenary session to share our findings. During the coffee breaks and the lunch, they will be served next door in the senior common room. I think many of you have seen this already to grab coffee this morning. The conference dinner this evening is not at 5:30, like I said in the email before, but it's at 6 p.m. It's at U of T's Multi-Faith Center. That's the address. I put this map on the website to hopefully help you find it. And one of us, I think Paul Schultz, will stay around here at 5 if you want to walk over together. at like 5:45. That's all for the logistics. For the first session, at the end, we'll do a discussion of what you think are the most exciting prospects for well-localized FRBs. I just shared a link to this Slido website, or Slido. In the Slack channel, you can already start contributing to this word cloud, but I also put on the QR code during the discussion so you can keep adding things to it. Vicky Caspi has kindly agreed to chair the first session, so I'll give the word to her. She'll say a few opening words from the Chime FRB collaboration, and then we'll get started with the talks. Thank you.
Okay, thank you very much. And while I agree it's disturbing when the team trying to localize FRBs cannot localize the conference venue, I'm really still very happy to be here and just thrilled with to see so many faces and looking forward to a couple of days of excellent science in thinking about how Chime FRB and other experiments worldwide can study and make progress on these mysterious objects. So that's all I was really going to say. Was I meant to? Should I say?
No, that's good. Yeah, no,
okay.
I'm just pulling up the slide.
Okay, great. Yes. Okay, so without further ado, the first talk will be given by Daniele Michilli, the astrophysics of FRB from their localization. And what I need is the schedule to know.
Well, this setup. Let me first apologize for my voice. And second, let me share how happy I am to be here. Right after the pandemic, my wife got pregnant and we got a beautiful boy, but that means that I haven't attended in person for years. And this is my first conference after the pandemic began. And boy, what a meeting to start. I'm so happy to be here. So thanks to all the organizers and of course to all of you to be here. And I kid you not, this is my birthday. And yeah, without further ado, let's start. I'm eager to present you what localizations can teach us about the origin of these fantastic and mysterious sources that are fast radio bursts. I wanted to start with some flashy, how can I go? This? Nope.
Work. Maybe you need to.
Yeah, it's okay. I can do it with the mouse.
No, it works.
Works?
The clicker works, yeah.
Thank you, Ziggy. But yeah, before going to the fun stuff, let me spend a couple of slides, boring introduction to say something obvious, but that I think it's important that it's explicitly mentioned at the beginning of this talk. Of course, localizing a source means to measure its position, but in this community, we often use it as anonymous for identification of the host galaxy of a fast radio burst. And of course, this is important as to use fast radio bursts as probes of the universe and gives us key information about the origin of the fast radio bursts, for example, to study their environments or to enable multi-wavelength follow-ups. And localizing, if you think about that, just means to reduce the uncertainties on the position that you measure. And so I put on the slide a general equation for the uncertainty on the position. And you can see that the localization is directly proportional to the wavelength that we are observing. And this is a parameter that we cannot play with a lot because other characteristics depends on it, like the field of view of the telescope. So what we can do to improve the localization is increase the baseline. This is what we usually do, which means basically to build some outriggers antennas that are apart from the core of the telescope and improve the localization in this way. Something that is often unmentioned is that the localization of an array also is also inversely proportional to the signal to noise of the detection, which means that the localization is better for a sensitive array. And actually the sensitivity has the same importance as the dimension, as the size of the array. Finally, let me stress out the importance of systematics that you can see in the second term. And you may notice that if you minimize the first term, then the systematics constitute, of course, a lower limit on the localization capability of the instrument. And I want to stress out that every team using a certain facility or a certain experiment should really study this second term, the systematics, with, for example, a bunch of known sources, a sample of known sources, and report it in some paper, in some form. In fact, I would argue that any localization is meaningless without studying and reporting this second term. Yeah, after this, for these first introductory slides, let me continue with a couple of fun facts. Even with very poor localization, we've had amazing discoveries. And this is mostly merit of the large sample that was discovered by FRB. For example, Paul Schultz in the room here was the first one to find out that we had detected a fast radio burst from our own galaxy. And the first clue that brought him to this discovery was the localization of the source, that even if it was only 1 degree, it triggered him to study this fast radio burst, and then of course found out the temporal coincidence with the magnetar flare, and later on this was independently confirmed by STER2. And another result that I found really cool, because it uses the large sample of CHIME FRB, but the poor errors on the position, is this presented by Raphael Ravendi et al., where we cross-correlated the position of fast radio burst with the large-scale structures in the universe. And again, even though the localization is poor, we were able to obtain some very good results. For example, we found out that most of CHIME FRBs come from a redshift between 0.3 and 0.5, and that there is a population of fast radio burst with very large DM contribution from the host galaxy. But after this couple of fun facts, I want to continue with the localizations, and I will go in order of precision, starting from CHIME FRB, because I think we hold the I don't know if it's so good record for most localizations with the least precision. And in fact, thanks again to the large sample, we found out that about 1% of the sources is close enough to Earth that we can place a limit on the redshift thanks to their dispersion measure. And with this technique, we localize, for example, one fast radio burst in M81, one of the closest galaxy. And this is, of course, perfect for follow-ups studies, as we will see in session 3 and in later slides. Other than, for example, to probe the halo of the Milky Way in a work presented by Amanda Cook and others that are in the room. We were able to localize other really close by fast radio bursts, most of them repeaters, in these works by Ibik, Bartwai, and Michilli et al. And what struck me is the diversity of host galaxies, even in this small sample. You can see that 2 are spiral, 1 is probably irregular. We have a beautiful example of a merging pair, and a passive spiral, which is a rare class of red spiral galaxies with very low star formations. Sorry about that. But now let's go into the real deal with localizations. And I will start with the VLA because, of course, it localized the first fast radio burst ever to a dwarf galaxy in this work by Chatterjee et al. And after that, we had other two localizations, and all of by New and Ravi, and all of these fast radio bursts were associated with persistent sources, which is not so common. So I don't know. Maybe it's just me, but I was struck by what is going on with VLA localizations and persistent radio sources. And other than this, of course, Cassillo et al. Presented this faint galaxy, and they built the real fast system that is providing us with these beautiful examples of localizations. But now I want to speak about ASCAP, which is leading by far the run for localizations, thanks to their amazing capability of localizing all the fast radio bursts in their large sample. And of course, follow Ryan's talk for more details, but here I just want to give an introduction, mentioning that in Bannister et al., they localized the first no-repeater ever, and follow closely by the second localization by Prochaska et al. And after this, we have the first sample of localized fast radio burst by J.P. Marquardt et al., which not only brought J.P. to derive his famous relation that we'll be, of course, discussing Xavier's talk after this. But it also allowed us for the first time to have a sample of host galaxies that we could use for statistical studies. And I'm going to present this in a separate slide in a moment, because now I want to continue with these discoveries. And I'm very sorry for the authors that I had to skip some of these amazing results, because each one of these would need a separate presentation, and they're also spectacular. But in this case, I want to highlight the central result by Ryder et al., where they localize a fast radio burst to a redshift larger than 1, proving that there are fast radio bursts that are indeed very luminous and energetic. And this also reminds us that localizations are the mean to measure the luminosity and the energetics of fast radio burst, another important consideration about the source emitting this. Finally, we have a couple of new facilities that recently joined the race for localizations, and Meerkat recently presented its first sub-second localization by Driesen et al. And please follow Tian's talk for more information about this. And of course, DSA 1010. I don't want to spoiler anything, but I know that they have some amazing results that Liam is going to tell all about. So here I've put a very personal list of what I consider some very exciting results about the origin of fast radio burst. For example, using the Makar sample, Bandari et al. Were able to identify most of the fast radio bursts in the galaxy outskirts, ruling out an origin from AGNs or cosmic strings. And also they found out that superluminous supernovae, which were a popular topic at the time, weren't able to explain the whole population. And also they found out that the host galaxies showed us a mix of old and young stellar populations. so that fast radio bursts probably come both from prompt and delay channels. And shortly after, Haynes et al. Found out that FRB hosts a very different properties that basically cover the whole parameter space of galaxies at moderate redshift. But they do not track clearly any known diagrams, except that there is a Green Valley excess. And the host galaxies do not track stellar mass, but the Mannings et al. Later found that fast radio bursts track the stellar mass within the host. So the host galaxy does, in general, does not, but the distribution of fast radio bursts within the host does. And finally, Haynes also found out that fast radio bursts are incompatible with all being emitted by long gamma ray bursts. I find very interesting the finding of Mannings et al. That they studied the distribution of fast radio bursts within the host, and they found out that they are clearly different from any other transient known. And so this may, it may suggest that there are multiple populations, or that they are not related to other sources of transients. And both cases are really interesting to me. And also, they didn't find a correlation within the host with star formation rate. So the place where a fast radio burst is found in a galaxy is the star formation rate in that region is not higher than the rest of the galaxy. Finally, in Bandari 2021, they verified that repeaters and one-off live in similar environments, that the host galaxies are in general moderately star forming with huge variations, and they cannot be explained as only coming from an old population. Also, another thing that I found very interesting is that they found out that the distribution within galaxies is incompatible with the distribution of neutron stars within our own galaxies, and also globular clusters, while they are compatible with other objects, and in particular with low mass X-ray binaries. So we are really starting to exclude and give indication of what the origin of fast radio bursts can be using these samples of localized sources. I want to conclude my talk with the best precision we can achieve at the moment, thanks to the very large baseline interferometry offered by EVN, and follow Brent's talk for a more truthful explanation. But for now, I'll just say that telescopes such as EVN cannot give us a large sample because of field of view and time on sky, but they can give us amazing precision on a few sources that can shed a light on the whole population. And this is the case, for example, of the first fast radio burst 1102 localized by Marcotte et al. And that was found to be collocated with a persistent radio source. And later on, thanks to the precise system that they developed, they found out that the third repeater that FRB discovered was localized in a near a star-forming region by in this work by Marcotte et al. And Tendulkar et al. Used very high resolution optical images to find out that it's located near a star-forming region, but not exactly on top of it, which gives us indication that maybe it was ejected by this star-forming region with some high velocity kick. Another very cool result by Kirsten et al. Was that the MAT1 fast radio burst that I described earlier was found to be in a globular cluster. So of course, very old population, but a lot of interactions among stars. And I think this is another very nice piece of information. And finally, Nimmo et al. Localized this very active repeater, and it was localized by many other instruments. And I think that other than for the physics of fast radio bursts, this image also gives us a relative comparison of the localization of different instruments. To me, two key takeaway points for localization of by EVN is again the diversity of the environment of these sources, but in this case, not only of the host, but of the local environment of the source. In fact, we see that some fast radio bursts live in a dense and turbulent environment with a very high star formation, while others are in a clean environment with low star formation. So I think I rushed through the talk. I thought I would have less time, but I will comment on my last slide of the talk about the future of localizations. And it's very exciting that we are actually living this future now, because new facilities are already joining the race of localization. As I said, DSA 1010, Meerkat, and others. And ASCAP, there are rumors and talks that ASCAP is going to increase the number of localizations of orders of magnitude, something that I'm very eager to hear during this conference, because I think this is going to be a game changer, as it's going to be a game changer, the upcoming Chime-out Triggers project, where we're building three trigger telescopes located across North America, which will allow us to localize every fast radio burst detected by Chime below 100 milliseconds. And please follow Kio's talk to know more about that, because we already have one of these stations that is online and looking at the sky, and part of the team just came back yesterday from installing the second station. And so I don't want to spoiler Kio's talk, but we will see some amazing picture and results. Finally, I want to conclude with what will happen within a decade. We have few planned facilities, some of them already founded, and they are expected to improve the number of localized fast radio bursts of an order or even 2 orders of magnitude. And all of them will have amazing localization capabilities. For example, we will have CHORD, which basically will update Chime, DSA 2000, which will update DSA 110, and a bit more in the future, SK in the Southern Hemisphere, and BURST in Thailand. And so I think this is a really exciting time and a perfect time to have this fantastic meeting. So thank you all.
Time for some questions.
I hope you could hear the talk at all.
Well, Chair, I ask one question. The diversity of the, you mentioned many sort of trends that seem to be coming out of the various localizations that have been published. And then later you mentioned, the identification of one source inside a globular cluster. I wonder if you would comment on, that seems to contradict with some of what was already previously concluded. I think we all sort of know this, but I'm wondering what your intuition is telling you that implies about the population.
Well, I think I don't know. Looking, this is a very personal opinion, but looking at the quantity of models we have for emitting a short duration, very energetic signal, probably there are many ways in the universe to emit these kind of signals. So I wouldn't exclude that there are different channels in which this can originate, and even in so different stellar populations and environments and so on.
Yeah, thank you. Any other questions for Daniele?
Or something.
Oh, in the chat.
Should I do that? I'll try. Can future sensitive instruments help discover FRBs in a wider redshift space to allow us to study redshift evolution? See if there is any. Oh, yeah, this is a very nice point. Yes, the upcoming facilities that I mentioned in the last point, in my last slide, most of them will increase our sensitivity of about an order of magnitude or more. And of course, increasing the sensitivity means that you detect further sources. And this will be incredibly helpful for cosmological studies. That's a very nice promise of these upcoming facilities.
Okay, question from Jason.
Yeah, I was just wondering, do you think there are any prospects for localization to kind of definitively show that there are multiple populations, either repeaters, non-repeaters being different, or what would be the kind of smoking gun evidence from localizations that it's one thing as opposed to another? I
think probably the best smoking gun that comes to my mind is multi-wavelength follow-up, because if you find a close by repeater that doesn't emit X-ray, or that you can identify a non-neutron star origin, that will prove that there's a different mechanism involved.
Question from Yuri.
Thanks. So in the same vein, when pulsars were first found, it was not always clear, but then there was one in the middle of the Crab Nebula discovered, and that was just from localization, a real smoking gun. Huh? And even if you say there's multiple populations, finding something like that would be interesting. I thought, I kind of hoped that by now we would have a few of these with the localizations we already have. What are your thoughts? Yeah. I don't know. This is already turning into a discussion, really, which is nice. What are we gonna do?
Yeah, that's a very valid point. But I think I'm trying of thinking to the history, for example, of gamma ray burst, that it took the community a while to distinguish between, for example, short and long gamma ray burst, and that is due to the distance, of course, much larger than the Crab. And probably also, again, due to the variety of environments that these things can live on compared to pulsars. So I think to do something similar that was done with pulsars, we need a larger population and probably more sensitive instruments.
Tarana?
Excuse me. So you mentioned this cross-correlation study with the CHIME FRBs that placed most events at this particular redshift range. And maybe this is more a discussion question, but I'm curious if you could comment on the unique redshift ranges for different FRB experiments.
Well, I think that Masoud is in the room, so maybe you want to take that one. He knows much better than I do, for sure.
Well, I assume that for next generations of experiments, we'll explore high redshifts, if there are any FRBs at high redshifts. I mean, it's hard to say, but with core more sensitive, we will be able to push it to high redshifts. Even with CHIME, I mean, we've seen FRBs at DM of thousands unit, and I assume that I mean, some of those FRBs might be due to the host. The DM contribution might be due to the host or foreground halos, but high redshift FRBs are expected, although rare. So.
Thank you, Musa. And well, at least we know at least one fast-radio burst at redshift larger than 1 as I present. Do we have time for another question from the?
Last question, yeah.
Yeah, Francis asking, what does it take for us to be convinced that the magnetar flare was a fast radio burst? And I think it's just the definition of a fast radio burst. It's my personal definition is that it's millisecond duration transient that is luminous enough to be seen from another galaxy and with our current instruments. And if this fast radio burst was emitted by one of the closest galaxies, we would have called this a fast radio burst, I believe. So I think, in my opinion, it's as easy as that.
Okay, we should thank Daniele again for a very nice talk. And our next speaker is Xavier Prochaska, who's going to be talking about FRBs as probes of astrophysics and cosmology.
Bon matin, je m'appelle Xavier. Je parle en français un peu, mais we'll stick with English. My Japanese isn't so good either. Good morning. Thanks for including me in this wonderful meeting. I've been asked, I think, to help set the stage for the two-day event and focus on this somewhat broad topic of astrophysics and cosmology with FRBs. I'm wearing my cat today, but I'm also here largely on behalf of the F4 collaboration. You'll see in the next two slides. And as the red circle indicates, I've now been indoctrinated into the CHIME experiment. I'm happy to be there as well. Two slides introducing the F4 team, a number of whom are in the audience. Get to know them. They're great people. Alex in the front row. I know some others in the back. As probably most of you know, our raison d'etre is to follow up FRBs, and we've been doing that pretty aggressively for about the last 5 years. A few more folks that we're recruiting along the way. So speaking of 5 years, what we have accomplished in 5 years on astrophysics and cosmology, it's been extraordinary, I believe. These facilities paved the way, or set the stage, I should say, it's probably the right way to phrase it, by localizing the first FRB and a few others. And then, of course, these facilities have really paved the way for the last 5 years, led the way. And I'll be highlighting some of the results that I've been most excited about from these work. First and foremost, what got me into this business, the correlation. I spent 2 decades pursuing the missing baryons problem unsuccessfully with just about every other facility you can imagine at our disposal. It's really FRBs that was the game changer. And the correlation satisfied at least Fukugita-san here that we could retire the missing baryons problem that he presented in 1998. I'm also excited in using FRBs to study intervening galaxies, what we often call the CGM, circumgalactic medium. We've been doing that with quasars and even other galaxies for quite a few decades now. FRBs, as I think most of you know, provide unique constraints, particularly on magnetic fields, which are not really accessible through our other techniques, and the density of the gas with scattering constraints. Also difficult to derive directly, at least from, say, quasar absorption line analysis, which I know very well. So these it's a unique opportunity to probe gas in the environments of galaxies. What else excites me? The ability to do that type of analysis on our own galaxy. The capital G here is our galaxy, galactic halo. The start of the year has seen 2 new results on this topic, fantastic results. On the left from the CHIME FRB collaboration with some large statistics, poorly localized, but still very valuable constraints on the Milky Way halo element. And on the right, a single source from the DSA 110 experiment, also placing an upper limit on the number of baryons within our own Milky Way halo. And I know as the years go by, we'll continue to refine those estimates. I've now changed my preferred value from 50 to 40 based on these new results. And of course, the trend might push me further down as we go. We've seen a new publication, likely the first detection of the intercluster medium with a fast radio burst. This is also from DSA 110 from Liam's work. They've detected at least 2 now FRBs within A-ball clusters, which is pretty wild. And as the right figure indicates, accounting for pretty good guesses or pretty good estimations of the components to the dispersion measure, one's left with a several hundreds contribution from the intercluster medium of that A-ball cluster. And I'm sure this will be happening in spades as we go forth in time. You've seen a publication on using fast radio bursts to study the magnetic fields within FRB host galaxies. When I give this talk into a general audience, I call them normal galaxies. They're pretty normal. They're primarily star-forming galaxies, as you can see in the left, but they span a large range in stellar mass. So they probe most of the star-forming population of the modern universe. And with the rotation measures that are encoded in the signals, one can infer or at least estimate magnetic strengths along the line of sight within those galaxies. And as we go forward, correlate that with the position of the galaxy and other aspects of the hosts. Pivoting a bit to cosmology, the work that I've been at least affiliated with has been constraining the Hubble's constant. The correlation has encoded within it, or an aspect of the correlation is the Hubble constant. So that's where some of the power comes from in this result. This is the figure published in James et al. It's not precision cosmology today. Sample variance dominates the uncertainty in this figure. We've since repeated the experiment, including a new parameter, which I'll show in a moment. The precision has gotten poorer. It's not so obvious here because sample variance does dominate. But this is a heads up. This constraining H0 is more challenging than we anticipated in the James publication. And the reason is H0 is highly correlated with another physical parameter, which we refer to as F. You're probably saying what the F is. F. It's a parameter of actually also, I want to make cosmology is a bit strong. Let's call it astrophysical importance. So the equation here is a formulation that Matt McQuinn introduced to describe the dispersion in the DM cosmic, so the cosmic contribution to the dispersion measure. And delta here is DM cosmic over the average. So that PDF was derived comparing to numerical simulations. Appears to be a pretty good descriptive physical variance in DM cosmic. And F is related to that sigma DM, which is in the equation. And there's good reasons to expect it to evolve like the redshift to the inverse square root. And so there's F. We had been calling it the feedback parameter, but Ron Ekers in the last craft meeting emphasized it's not all about feedback, it's about structure of the universe. So I'm gonna stop calling it that. If anyone has a good name for F, kindly pass it on to us and we'll start using it. So intuitively, or maybe more than intuitively, descriptively, this is a figure from Jay Baptista's paper, which we'll post probably the next month. The top figure shows a large value of F, so that means a large dispersion about the mean of the correlation, and the bottom figure shows a low value of F. So that's in a cartoon way, that's how F changes the distribution of DMs that you would have observed in a survey of fast radio bursts. There's power there. Obviously, we have data that can constrain this, and this is the main result from Jay's paper. There's a today's constraint on this F parameter from 20 well-localized FRBs and 70 not so well-localized FRBs. And this is one estimation, the blue dashed line from a numerical simulation of what F might be in the universe, in their make-believe universe, with some prescription for feedback and galaxy formation. Quite consistent with it at this stage. So that was a whirlwind of what we have accomplished in 5 years. If you're part of one of these surveys or any of the others, give yourself a bow, take a bow. That's pretty amazing progress in just a few years. What we're thinking about, I think, in these 2 days is what can we do with n greater than 100 FRBs, well localized. When I give this talks on FRBs, I always show this figure, which shows the exponential rise in both the number of unlocalized, or sorry, poorly localized, or is that too negative? Not so well localized FRBs, of course, driven by the CHIME FRB survey, and we've recovered far more than 500 at this stage, as you know. And then even in the localized component, there's an exponential rise, largely due to craft ASCAP, as we heard in the previous talk, but there are new surveys turning on right now, or have turned on. And that red curve is going to continue to rise exponentially for the foreseeable future. So what can we do with hundreds, or dare I say, thousands of FRBs? This is this all-sky map of the CHIME FRB population of roughly 4,000 FRBs. One of the things that excites me is to probe M31's halo. The blue blob in the lower left is a model of the dispersion measure that could be due to M31's halo. And I think you can see that as we're getting to thousands of sources, even not so well localized, one may be able to infer its properties. How about not just detecting the missing baryons, but determining where they're located within the cosmic web? This still drives my scientific interests, and one of the surveys I'm involved in is called FlimFlam. KG Lee, Ilya Kirkin lead that effort. This is a 2-point correlation analysis between FRB positions and foreground galaxies. This figure shows an example of probing the foreground galaxies in a so-called wedding cake type analysis or survey, where you go wide and shallow with smaller telescopes like the AAT in Australia, and then deep and narrow with bigger telescopes. And I asked Ilya to generate a forecast. So kind of the next series of slides are mainly forecast figures, what we might be able to accomplish. This is a forecast with 200 well-localized FRBs with galaxies surveyed, similar to what I just described. It allows for the host contribution to be log normal with those parameters. And you can see one can constrain the fraction of gas that you would associate with the true intergalactic medium gas between galaxies, as opposed to the gas close in and around galaxies, CGM. And also at the same time actually place a nice constraint on the host properties. I'm excited about what we may do, what we will do, learning about ISM turbulence and CGM density profiles from scattering measurements. Here again is another area where one will benefit greatly from hundreds of localized FRBs, at least for the part that excites me, to identify intervening close by galaxies, but one can also probe into the interstellar medium, the host itself. Here's a forecast of what one can do for this F parameter with 100 FRBs. This does have, trust me, this has strong astrophysical significance for constraining galaxy formation models. The two gray curves show different determined H0 values. Let's assume gravitational waves or some other technique will nail that without FRBs. Then you can quite tightly constrain F from even just 100 FRBs. And distinguish between models of galaxy formation where you're ejecting all your baryons outside of galactic halos compared to those where majority of the baryons stay within the dark matter halo. Not to give up on H, not altogether, with a 20% constraint on F, say from Flim Flam or other 2-point surveys. There's precision one can attain on the H naught parameter, something on the order of 5 to 10% with 100 FRBs. At least until we add another parameter that we weren't aware was so degenerate with H naught. I think we've identified the worst one so far. I think there will be opportunities to probe helium-2 ionization. That's the last major phase transition of the universe, which we know occurred around redshift 3, a little bit less, from quasar observations. I think FRBs will have an opportunity to play a role here as well. Having redshifts will have additional power, whether that's the most promising technique or just large populations remains to be seen. There's wonderful opportunities, as many of you know, and I'm not an expert in this, to use FRBs, lensing of FRBs to constrain astrophysics and aspects of cosmology as well. I'll defer to the experts on that topic, but let's not take our eye off that ball either. And opportunities to study IGM magnetic fields in the era of many hundreds and thousands of localizations. And if you haven't seen this paper because it's not online yet. Most of you have not seen this paper. I know a couple of you are the referees of this paper. I'm looking at you, Jason. And Kyo. I think you're the referee too, right? I'm not at all involved. But Matt McQuinn, sharp gentleman and that he is, and his mentee, who's now I think working for Google, Boone, they've thought about what a new generation FRB experiment will do for cosmology. As Matt put it to me, something last week, he was trying to think of a way to improve cosmology by an order of magnitude, and was frustrated with the kind of slow approach of just let's do another DESI experiment or something like that. So he dreamed up this. Let's put 3 satellites into space that detect FRBs. Let's separate them by about 10 AU. Let's make sure they know each other's position to a centimeter. And there you go, done. And I'm sure he's right, or the referees agree he's right. It's a 30-page, this is a Chime AppJ letter. 30-page AppJ letter, I'm told, yeah. But let's do it. I'll be retired. You do it. Get to it. I think it is the most promising path forward for cosmology with FRBs. Distance. So because the wavefront is curved, circle, you measure the distance geometrically, and then you have the redshift too. Yeah, clever, huh? All right. So what could ruin this party? Hopefully nothing. But here, these are things that keep me awake at night, I guess. The host DM it's a nuisance for me. This is a plot of the log normal with our current best estimates of that function. And yeah, you can see 1% of the FRBs have DMs greater than 500, at least according to this log normal distribution. That's a nuisance. That does play a role in most of the analyses that I part in. I don't think we've taken real care about this one yet. There are going to be false associations. When you get to 100 FRBs and you've got a 99% confidence of association, you've got one false association. And that's if you're doing 99% type level. So how are we going to fold that into our analyses? Let's get started on that. We need to. Non-detections. And what about when we can't the redshift. How does that affect our analyses? We had to, for the H-naught analysis of James et al., we didn't punt, but we didn't, well, we had addressed it, but not in an elegant approach, not an optimal approach, let's call it that. So how are we going to fold that in to these types of analyses? And then there are for sure biases in our samples. We're aware of some of them. We see them empirically in some cases. The orange curve is the solenoid distribution of the Kraft ICS population. You see at the low solenoid end, it does not follow the curve. We're missing of order 2 times the FRBs down there than we should have had. And I don't know, put Ryan on the spot. Do we know why? Yeah. So these are things that should keep us up at night, and these analyses as well. Hopefully we should be able to understand. If we can't even understand them, then we really have to be working. Okay, but and on a maybe positive note, 5 minutes, I'm done. I've shown slides like this. You've seen this slide at the last, was it FRB 2022? I think I did some updates. Yeah, I made H not worse. I remain bullish on the left column, pretty optimistic on the center column, and I'll say pessimistic on the right-hand side. But still, the future is wonderfully bright. We do have some work to do as we go from results that are sample variance dominated to not sample variance dominated. The systematics that I described at the end will certainly matter in n equals 100 samples and beyond. Thanks.
Okay, thank you very much. Lots of time for discussion. I see Masood has his hand up. Masood?
Thanks for the talk. Looking at the DMZ plots that you showed when you described the Hubble parameter constraint, it seemed as if the parameter F captures the host DM contribution as well. Like, I'm wondering, does it capture DM host like the in the log normal distribution, or do you assume like a fixed model for the host contribution here?
So in these plots, this includes a log normal host contribution for sure. All of the statistical power, I was describing this to Jay and Alex last week. Most of the statistical power here is where there's a sharp feature in the distribution, right? So we refer to this as the DM cliff. That's where the power lies. So DM host, the nuisance that it is, lets you discover FRBs up here at your leisure with no power on the model otherwise. But down here, the lowest DM host can be is 0. So that's why this becomes a cliff. And so it's really, for these types of analyses, it's the distribution of FRBs at this lower bound that makes all the difference to the result.
So what's the physical significance of parameter F? What does it capture physically?
Yeah, I didn't put in the cosmic web. So picture your favorite cosmic web illustration from computer simulations, right? In a universe that was perfectly homogeneous, you would get the same DM cosmic value to the same redshift every time, right? There'd be no variation in DM cosmic. But you've seen a cosmic web movie, you know their structure. And so there's variations around the mean. F is capturing that.
Thank
you. Okay, Daniele, you had his hand up?
Connected to this, could you disentangle the two with a sample of Astro bars large enough? And did you do some calculation on how many you need, if so?
Distinguish between F and H naught? Sorry.
F and H.
Yeah. So this, that forecast adopts a 20% prior in F, which I'm assuming we're capturing from some other analysis, say the 2-point correlation analysis. Okay, but if I don't have a prior on F, that's the gray curve. That's the best you can do with 100 FRBs. Can you do better with 1,000,000? Yes, you'll do better with 1,000,000. We can, yeah. Let me run an analysis with 1,000,000. See what it looks like. Sorry? I'm not going to claim it scales with a number. It should. I don't see why it wouldn't. But as other folks in the audience know, eventually you'll hit uncertainty in the next unknown parameter, which is the fraction diffuse baryons. I would call it the little f problem.
Okay, we'll go Keo, Liam, and then Mubdi.
So what's Ron's objection to calling F a feedback parameter? Because I mean, yeah, it includes all the structure of the universe, but all the uncertainty in the structure of the universe, like we know what the dark matter is doing, right? We know what's happening on very large scale. All the uncertainty in the structure of the universe for the ionized gas is from feedback, right?
Yes. Ron, he must appreciate that, but yes, I agree. You'd have to ask Ron.
Okay.
I don't like calling the feedback parameter because it's inversely proportional to feedback. More feedback is smaller f. But
So
right away.
all right.
That's bad.
Sure. Okay. I mean,
yeah, Ryan reminded me that Ron also said, well, maybe there's something else out there in the universe redistributing baryons, not galaxies.
Okay, Liam.
So, I mean, you can call it the fluctuation parameter. It's sufficiently generic. That captures everything.
Done.
That's the math cal F.
Fudge factor.
So before we get DESI and before we get Sphere X, and we have these large spectroscopic or quasi-spectroscopic galaxy surveys, what's the order of magnitude number of FRBs that we can follow up each year in OIR?
For individual redshifts or for the flim-flam type experiment?
Yeah, so ignore the foreground mapping. Suppose we just want host galaxy redshifts. How many do you think we can get?
Hundreds per year.
Okay. That's more than I would have guessed, so that's good.
I'm after 1,000. Fast.
Okay, Mubdi.
So presumably that fluctuation parameter, if we're going to call it that, is going to sort of encode some information from the cosmic bias as well. So
good one.
I mean, is this going to be something that either, stops us in our tracks, or is it another unique probe to figure out, potential hosts or differentiation between the hosts of, high redshift FRBs?
Right. We have, if we have yet to include sigma 8 in our analysis, changing sigma 8, we should be. I think there's going to be power there too. Yeah.
We still have time for discussion. Jason.
Clancy has a question online.
Oh, I don't see the.
Clancy, you should be able to unmute yourself and ask your question if you like.
Okay, I hope you can hear me.
We do.
Yeah, my question X was on slide 11, you were showing the P cosmic models. But do you think in this field we're always going to be tied to fitting models? Or do you think there's prospects for simply measuring the structure of the universe directly with this in a model independent way?
Yeah, I think what you're asking is there a non-parametric way to describe the variance in DM cosmic?
Yep. Well, for us to measure it, right? I don't care if we're describing it via simulation.
Yeah, as a function of redshift. Nothing quickly comes to my brain. Nothing quickly comes to my brain. I think we're going to be sticking with this for a little while. Yeah. I'm open to other ideas.
In business. Good to hear.
Oh, Mohit has a question online. Mohit?
Hey, X, I think you kind of answered my, not exactly, but you just alluded on to my question. So I have this question that for quite some time, that the measurements of F, that which basically is a feedback parameter in analysis, and Hubble's constant is kind of not completely independent. And I think you just said that because F and sigma 8 are likely degenerate. So I'm just wondering that when you do you take this into account when you are constraining H naught?
So unfortunately, I did not include one of the other figures from Jay's paper. F and H naught are so degenerate, it's painful. We have yet, it must be mathematically demonstrable. But I'll send you the figure, Mohit. That's as good as you can see today, and you can see how tightly degenerate they are.
I see. So this will always be a constraint
Insofar as that PDF that Clancy was just calling into question is a good description, it's that degenerate.
So does that mean that unless we have a independent constraint on F, the Hubble constant measurements from FRB side will always be a little uncertain?
Yes. They do. The degeneracy is not perfect, of course. But yeah, the gray line is as pessimistic as it gets for 100 FRB. Well, as pessimistic as I think it gets for 100 FRBs.
Okay, time for one more question, Jason.
Very different type of question. Have you thought about how many FRBs would you need to precisely localize to see that there's a subpopulation associated with the globular cluster systems of galaxies?
I have definitely not, but I bet those that discover
you have a
the
student
globular
who will
cluster.
do this, or yeah, okay.
Sorry.
Okay, well, I see on the schedule that we're headed into a 15-minute discussion on actually just these topics. So why don't we take a moment to thank our wonderful okay, and so the question that we're meant to discuss now for the next 15 minutes is what are the most exciting prospects for well-localized FRBs? And just requesting how would you want us to do this? Is that something I should?
Yeah, so one way of contributing, I shared my screen with the Slido, so you can either follow the link on Slack, or you can go to slido.com and fill in the meeting ID over there, or you can try to scan the QR code, and then you can just type your favorite prospect for well-localized FRBs, and we can see what everyone's excited about, and maybe that will steer the discussion, and otherwise people can just speak up and say, here's my favorite thing, and others can reply. As a reminder, everyone on Zoom should be able to unmute themselves or raise your hand if you'd like to speak up. We can hear you very well in the room.
You're pointing at some. Oh, Keo, yeah, okay.
Yeah, so I just wanted to say that, I mean, I think the previous the questions from the previous talk were kind of pessimistic about doing cosmology, and that things are so degenerate with this, these astrophysical parameters. I would turn that around and say, the astrophysics of large and intermediate scale structure is so hard. It's actually like harder than cosmology. So we're like, this is an opportunity for us to do something that you can't do with DESI or with, or with other cosmological probes, right? I mean, I think, for us to do H naught is like just going to be really hard. Like, if we solve F, we're going to run into little f, we're going to run into a redshift evolution of DM host. Like those are just, I think, at the percent level you need to do H naught, those are like kind of unsolvable or very hard to solve problems. Whereas, feedback and intermediate scale structure, these are problems that are just completely intractable from other probes, and are just so uncertain in the universe right now. And it's just a huge opportunity for us. So I mean, I think I would at least like to see the discussion recentered away from pessimism on cosmology and like optimism on doing astrophysics that just no one else can do at all.
Yeah, I guess I'd like to amplify that in a slightly different way. I think in the era when we have hundreds of localizations, in particular in the question of the diversity of the different host types and you know, how we can decide if there's multiple different FRB progenitors. I can imagine that what the diversity is telling us right now is that, oh, maybe there really are different classes of FRBs that in some of these analyses we sort of just mix together because we don't know how to separate them otherwise. But in the area where you have hundreds of them, maybe we'll start to see sort of islands forming in parameter space of galaxy properties. And maybe you'll start to see, oh, there's a clump of them that are in, you know, the Green Valley, and there's a clump that are in star formation region, a clump that are, and then you can actually split them off by their associations. And then maybe certain subgroups will be better for some of these applications than others. Casey.
So I'm always interested in the question of the oddballs versus the populations, and I think kind of curious to gauge the sentiment in the room, but I think we're always motivated to talk about populations and homogeneous follow-up and uniform, and that's sort of what the first talks were focused on. But it seems like the oddballs are still dominating a lot of the big results that are coming out, and I wonder if people feel like that trend will continue for a long time, or we'll be talking about populations to motivate our follow-up campaigns and convince the tax to give us time. But in fact, all the big results are in fact the 1 out of 100 that are really peculiar astrophysically. And maybe even that's relevant to feedback and fluctuation science too, where there's maybe the very low nearby host associations telling us about peculiar local environments.
Yeah, well, I think pulsar astronomers have thought, you know, spent years both studying the nature either of pulsar emission or of pulsar populations, both in dual ways, from the jewels of the population, the amazing whiz-bang binary pulsars or other, you know, intermittent pulsars tell you so much, but then also the population studies are huge as well. They tell you, so I think it's always going to be a little dual. Paul.
Yeah, I was just going to point out that it doesn't necessarily have to be a dual. An important part of the oddballs is comparing them to the population and say, is this oddball property, you know, 121102's extreme rotation measure, whatever, does it match with the population? And that can guide you, you know, in what it tells you about the population.
Yeah. Somebody online, yeah.
I've got a Clancy if that's the person.
Oh, sorry, your hand's up. Okay, I couldn't see it from this angle. Clancy, go ahead.
Yeah, it was just a comment previously about the big results from oddballs against population modeling. As someone who does population modeling myself, maybe this is a little bit of a bias because population modeling is a boring, statistically detailed, unrewarding kind of venture where you have to make a bunch of assumptions. And there's no way you can get a boom, here's the result, right? Whereas if you do see one oddball, well, it's there, you know, this is astronomy. We do get dominated, you know, traditionally dominated by new discoveries. And obviously, if you're looking at populations and trying to work out, okay, are we consistent with 1 or 2 populations? This is a slowly evolving thing, right? You look at CHIME's evidence for different width distributions for repeaters and non-repeaters, right? I mean, that story is still unfolding. I don't think the chapter's closed there, but evidence slowly builds. Whereas if you have one single new thing, well, that goes from 0 to 1 is huge. Like 1 FRB from a globular cluster can change things. So I do think I'd like to put up the hand for saying that the modeling populations and so on is very important, but the nature of the work doesn't lend itself to individual big results.
Yeah, I guess I feel like a lot of FRBs are associated with star formation. So even though they're coming from different types of galaxies, all these galaxies are forming stars. So I'm a bit less sort of pessimistic about, you know, multiple populations. But then I guess the other part of the story is like the historical part of it, you know, doing all these host galaxy follow-ups. Like when we first did 180924, we didn't know if it was like lenticular or an early type spiral galaxy. So the paper said, you know, it could be either of these things. And you know, people said, oh, that means it's an old galaxy. Whereas when we started to go look at it even with HST, with Alex's work, you could see the spiral arms, right? So it's gotta, you know, so there's then, you know, the Green Valley aspect of it. The recent work by Alexa, who's somewhere. showed that, they're more closer to the star-forming main sequence than we initially thought. So this part of this is like still having a small number of statistics.
Please.
Hi, I'm Anya Nugent. I study short GRBs, so a little bit different. But I was going to say that when we're looking at the short GRB host population right now, which is pretty well defined, we are specifically going after the really oddball cases of host environments to place the deepest constraints on how their neutron star merger progenitor is forming. And so potentially looking after like dwarf galaxies, which would be really unique because then we could potentially get like the most minimum delay time or formation time scale, which is unknown in GRB stuff. But then also I wanted to mention that GRB 211211A, which was the long GRB associated with a kilonova, was a really fascinating event because it's opened up this whole new world for GRB astronomers of looking at long GRBs as being our process producers and major producers within the universe, which was not something we necessarily thought of before. So I think, at least in GRB science, the oddballs are the most exciting to look after.
Jason?
Yeah, so on the topic of exciting prospects, I mean, so X mentioned the solar system VLBI system. That's going to be ways down the road. But if someone can find a strongly lensed repeater, even with, just global VLBI, you can do some pretty amazing things. And Olaf Wucknitz had a paper about that, right? Doing kind of real-time cosmology with the strongly lensed repeater, looking at delays and even imaging the lens copies. That would be the most exciting thing for me, at least.
Okay, we'll do Mubdi, then Kia.
So on the other end of the distance spectrum, something that is close enough that we can see the individual source, right? Something that's local galaxy, Andromeda, Milky Way, LMC, SMC, right? If that happens, and knowing, all of our biases against detection for something that's super local, it would really open up. It would be an oddball of a different sort. It'd be an oddball in the sense that we can actually see the physical thing that's causing it, and that would open up a lot of discovery space potentially.
Yeah, I just didn't want the strongly lensed repeater comment to go by without there being a mention of Whaley's like burst project, because there's not a lot of representation here. I'm not on it, but that is the array that's kind of optimized to do that science. So there is an array being built that's optimized to do that, and that complete with VLBI outriggers. So it's nice to hear that there's interest in the community.
Do you want to just say a sentence or two about what makes it optimized for that science?
Well, just the fact that it's so, Liam will probably know better than I, right? The exact parameters and stuff, but it's just so wide field that it has a hope. It's enough of the sky that it has a hope of seeing the lens repeats with sort of the week-long, the probability of seeing both images from a lensed FRB is small because they're separated by like a week, and our field of view, even for CHIME, is 200 square degrees. So if you want to have order unity probability, you have to see order unity of the sky, and that's what burst is designed to do. Is that right, Liam?
Would be for gravitational lens FRBs, you get a lot of optical depth, so probability of lensing from high redshifts. So you really want to be probing a large volume, distant FRBs, and you need this order 1 sky covering fraction as well. So burst 2048, I think probably won't find these sorts of systems, but if you scale that up twice, then you could. Or you take a very sensitive telescope and you point at the NCP forever.
Wait for the microphone. You can give it to X. Yeah.
Do you need, I'm showing my ignorance, do you need the redshift of the source to proceed with the science?
Yes. Daniele?
Yeah, on this subject, actually, I'm preparing a paper that I hope someone of you will review soon. So something that I think we're not considering on the lensing side is the upcoming optical surveys such as LSST and Euclid, which will tell us basically immediately if one of the localized fast radio bursts will be lensed and when the second image will appear. So I think that the prospect there could be much brighter than what anticipated in your slide access, because of course you can target that with a different telescope. You don't need like to cover the whole northern sky with a single telescope.
Sir, oh, Ziggy?
No, there's a question in the chat from Zoom from Sachin Pradeep. Do you want to speak up, Sachin, if that's possible?
Hi, yeah, thank you. So my question is like, first question is how can we monitor these delays? We have, there was a recent paper by Rabbi et al. In 2023 March, where he was quoting certain time delays, but especially for strong lensing FRB.
Or can you, I'm not sure I got the question.
No,
Can you
I think the question is if someone has thought about strategies for monitoring finding lensed copies that are a few days later.
So sounds like Burst will be a good telescope for that. And yes, and what Daniele said also.
Yeah, so this might take weeks and months for the delays would be, and there are high chances that we can miss it, right? So how are we gonna monitor this?
Yeah, so I think there are three options. You can either have an all sky monitor where you see the same patch of sky all the time because you're covering, a steradian or something, or you can point at the NCP. So again, you always have the same field of view. Or you can do this sort of forward modeled guess at when the second pulse is going to show up, like what Daniele just described.
Okay, and sorry. Yes.
Sorry, I have one more question. Can I?
Okay, very quickly, please.
Yeah, thank you. So, there isn't there a possibility that the lensed pulses are gonna be affected by the lens galaxy because it's yeah. So how are we gonna model that?
Yeah, for sure there will be additional scattering from the lens, but hopefully most of the lenses will be elliptical, and so the scattering might be manageable.
Thank you.
Okay. Out of time for discussion, and we can continue this very interesting discussion over coffee. And I just think we should take a moment to thank all the speakers and everyone who contributed.